So usually we start by thanking the organizers for inviting you and so on. Usually I forget to do that. Today I will not do that. I mean, Antoine said that being a heritage speaker was impressing. I disagree with that. It's totally depressing, you know. I was visiting my parents this weekend and I told them, you know, it's official that I'm old. Holly Krieger and Charles Favre and Romain Dujardin and Thomas Gauthier, they decided it's official. I'm a heritage speaker. So. And then my parents, they started to laugh and laugh and laugh. And then they said to me, did you see the initials? Okay, so in French, it's hors service, which means out of order, you know? Okay, so now that I say that, I will try to give my talk. So it's rigidity in algebraic dynamics. Okay, and so what I want to do is I want to list 2-3 open questions which I think are interested of different kinds. But before I do that, I want to discuss what is rigidity, okay? Because I ended up writing a paper about rigidity in holomorphic dynamics with Romain. And in fact, I realized I don't know what rigidity is. And maybe Romain knows what it is, but in fact, I want to start with examples of rigidities. So rigidity phenomena. And I don't want to start with dynamics because I think thinking about rigidity, the first and the main example of rigidity I know of is Cauchy theorem. So it's example 1. Okay, so you are in 3 space and you take 2 convex polyhedron, okay, with the same combinatorial structures. So you have the same number of faces, of edges, and the way you glue them are the same. And you have isometric faces. You are in R3, or in fact isometric, globally isometric. Okay, so I give you triangles and things like that. I tell you how you should glue them, and then you do it, and the result is not flexible. Okay, if you can do it in 2 ways, in fact, you can go from one way to the other one just by a rotation of R3 and translation. Okay, so that's the best rigidity statement I know. Okay, there is just one way to construct your object. Okay, one way up to what? Up to a global isometry of the ambient space. Okay. But there are constructions by Conley and Stephan. There are non-convex, flexible polyhedron. And you can also construct such examples which have topologically are spheres. Okay, so it's not convex, because otherwise it will be rigid, but it's homeomorphic to a sphere. Okay, so you glue some triangles. What you get is like a sphere with, how do you say that? When you push the sphere and it's not convex anymore. And then the result is something, it's a polyhedron, but you can move it, you can move the angles of the faces continuously in such a way that you get a family of polyhedra which are not isometric one to another. Okay. But when you do that, all flexible polyhedra, let's say, which are spheres and bounding a ball topologically, they have a property. The property is that the volume which is contained inside the polyhedron is fixed along the deformation. And it's even better if you want to go from one polyhedron to another one just by slicing, cutting the polyhedron and gluing it again. You have to preserve the volume of the total solid polyhedron that you have. And there is a better invariant, not just the volume, it's called the Den invariant. And the Den invariant is invariant under deformation. Okay. Okay, so that's the first example I know, and you see it's the best example you can think of because you have rigidity statements, you have deformation statements, and somehow you can easily parameterize the space of deformation, and there are things you understand well which are invariant under deformation. Okay. So the second example I'm aware of is the theory of lattices. Okay, so let gamma be a lattice in a higher rank Lie group, say SLM R, where M is fixed, is some integer at least 3. Okay. Okay, what is it? It's a discrete subgroup of SLM R, such that when you take the quotient of this space by this discrete subgroup, you get a manifold, and the manifold has a finite volume for the R measure on SLMR. Or if you prefer, it's a discrete subgroup of SLMR, such that in SLMR you can construct a subset of finite R measure, such that the translate of this set by the elements of gamma cover SLMR. Okay. And now we want to understand what are the subgroups of SLMR which are lattices and are isomorphic to gamma. Or even what are the subgroups of SLMR which are abstractly isomorphic to gamma. Okay. And so you have the work of Calabi and Vesentini. And the work of André Weil, so it's roughly around the 60s. And such lattices are locally rigid. Okay. And here I want to spend some time on this. What is the meaning of that? So if you try to deform So you look at gamma abstractly as a group. It's finitely generated, that's the first result. Okay. So you can fix a finite number of generators. And then the generators correspond to matrices in SLMR. And you ask yourself, can I move a little bit the coefficients, the entries of my matrices, and still get an embedding of gamma in SLMR? Okay. Of course, you can do that. You can do it by just conjugating all elements in gamma by a small matrix in SLMR. But that's the only way to do it. Okay, so that's the result they proved. Okay. And to do that, you have to build a good moduli space for your problem. And so this is called the character variety. Okay, so you look at all representations, or if you prefer, whole homomorphisms from gamma to SLMR. Modulo the action of SLMR on itself by conjugacy. Okay, so and then you can take the quotient in the sense of algebraic geometry. Okay. And what is hidden behind this theorem is compute. So one step is to compute tangent spaces to this. Okay, so if you show that this variety, which is an algebraic variety, has dimension equal to 0, then you have some rigidity result. Okay. And then, of course, after that, there is the work of Mosto and then of Margulis. It's much better, you understand completely all homomorphism from gamma into Lie groups. Or let's say in linear algebraic groups. And I don't want to enter into that, but it's called super rigidity. Okay, somehow if let's say G is SLM of R, the same M, then you just have a finite number of homomorphisms. You can up to conjugacy, and you can describe all of them. Okay. For instance, SLMZ, you can embed it as SLMZ is a subgroup of SLMR, or you can twist it by the automorphism, which is you take a matrix and you map the matrix to the inverse of the transpose of the matrix. And that's it. Okay, so here again, you need a nice moduli space. So this is the moduli space for your problem. And you have local rigidity theory, and you have much stronger global rigidity results. Okay, and now I move to dynamics, and the main examples I know. Okay. Yeah.
For the lattices example, when you say such lattices are locally rigid, what do you mean such lattices? Like,
so an example of a lattice is SLMZ. Okay. And so SLMZ is generated by elementary matrices. And now if you move a little bit the coefficients of your elementary matrices, they are not elementary anymore, and you assume that the group that generate is abstractly isomorphic to SLMZ, then in fact the group is conjugate to the standard SLMZ by an element of SLMR. Okay, and so in dynamics, I think one of the best examples I know is diffeomorphisms of the circles, of the circle. And here, the one important result is due to Hermann. I think it's around 6. Yeah. So it goes in two parts. I want to state two statements. The first one is that if F is CR diffeomorphism of the circle, preserving orientation, Okay. Let's say with R at least 3. And now you assume that the rotation number of F satisfies a certain Diophantine condition. So I don't want to make it explicit, but it says that this number is not too well approximated by rational numbers. Then F is conjugate to the rotation of this, of angle equal to this number by a smooth diffeomorphism, CR minus 2 diffeomorphism. Okay, so you just have one number to extract from the dynamics, and if this number is good from an arithmetical point of view, then the map is completely rigid in the sense that it is conjugate to the rotation. Okay. And here you see nice features which are specific to dynamics. For instance, an issue is to determine the degree of regularity of the conjugacy. Okay. So maybe rotation number. Yeah, I stated it wrong. Yeah.
No, it should be close to the rotation, right?
No, I don't think so. For Hermann, I think for Arnold you need it close, but for Hermann you don't. No. Ah. Okay. Is it a joke or is it true? Okay, and okay, if R is, so if you have infinitely many derivatives, or if the map is real analytic, then the conjugacy has the same regularity. Okay, I mean infinity minus 2 is infinity. Okay, and this statement goes with another result. So you see, it's a problem about conjugacy. But what comes with the proof of Hermann is also a theorem about ergodicity. CR, let's say C2 diffeomorphism of the circle with irrational rotation number is ergodic for Lebesgue measure. So it does not preserve the Lebesgue measure, but what I'm saying is that if there is a set which is invariant under your diffeomorphism and has positive Lebesgue measure, then this set is everything up to measure 0. After the talk, okay. But what I can say maybe is what is the rotation number? I'm not sure everybody knows it. Okay, so I mean you have the circle, and you have a homeomorphism of the circle, preserving the orientation, and you take a starting point x0, and you look at the orbit. X1 is f of x0, etc. So you x2, x3, and then you look where is the next one compared to the previous ones. Okay, so for instance, in my example here, the first, I mean x4 is between x0 and x1. So, okay, so this you keep in your head. Okay, and you continue and do it again. Okay, and you fix some time n, capital N, and you look for rotations which do exactly the same. Okay, so you are looking for angles theta such that the rotation of angle theta has the same combinatorial structure starting with any given point. Okay. And then when n goes to infinity, the number of theta which are possible is decreasing. I mean, the interval you get is smaller and smaller, and at the end you get some number, and this is a rotation number. Okay. Okay, so here I wanted to insist on two facts. The fact that when you look at this type of question, in dynamics, the regularity is important, and simultaneously, usually you prove results which are really about the dynamics. Then I want to move to anodes of maps. Okay, so you take M compact manifold. And F from M to M, a diffeomorphism. Let's say diffeomorphism. And then you say that it is anodes if you can split the tangent bundle as the sum of two subbundles, the unstable subbundle and the stable subbundle. So at every point x, you have a splitting in a sum of vector subspaces. Okay, but the dimension does not depend on x. You know, it's a subbundle. And what I'm asking is that it varies continuously with x. So that's the first thing. And the second thing I'm asking is f dilates the unstable subbundle and contracts the stable one uniformly. So for every v in the unstable subbundle, f star of v is less than, or is at least lambda of v. So here the norm is for some Riemannian metric on your manifold. Lambda is larger than 1 and does not depend on v. Okay, and you have the same for, let's say, the inverse of f. Oh, sorry. And you have the same for the inverse of f along the stable manifold. Okay. And then here you have automatically local stability. Okay, so if G is a diffeomorphism of f of M, which is sufficiently close to f, then G is an OSEF, and G is conjugated. To F. Okay, so sufficiently close, what do I mean by that? I need to keep this kind of, I mean, I want to make sense to this type of definition, so I need C1 close. But the conjugacy is just C0, is by a homeomorphism. Okay. In fact, if it is C1 close, it's isotopic to F, and the conjugacy is isotopic to identity if I want. Okay. And here, this is why I skipped your question, Milan. Here it's easy to see that there are examples such that you have a C0 conjugacy which is not C1. You just start with a standard Anosov map. So you take a linear transformation of a torus like 2, 1, 1, 1 on R2 but Z2. And then you take a deformation of that, so you, in the space of diffeomorphisms, such that the origin is still fixed, but the differential at the origin is not conjugate to 2, 1, 1, 1. Okay. Then you cannot have a diffeomorphism that conjugates the two transformations, because otherwise it should conjugate the differential at the fixed point. Okay. And also, so I will just say it, not state it, but this type of result also comes with some understanding of the dynamics. Here it comes with a shadowing lemma. So if you have a notion of approximate orbit, which is notion of epsilon pseudo-orbit, then every approximate orbit is approximated by a true orbit. Okay, so that's the shadowing lemma. I won't write it because the time is running very fast. But again, this is a typical instance of rigidity result, which comes with a better understanding of the dynamics. Okay, so the shadowing lemma. Okay, I will use this blackboard. No? Yeah, the organizers are principal ultrafilters, dictators. T2, T3. Okay, so then I want to list what from these examples, so rigidity problems, I think it's good to say that it's not a problem, it's a way of thinking about dynamical systems. And the first thing to do, which in certain situations has very good, are very good, and in certain cases it's very bad. I mean, it's, do we have good moduli spaces? And in dynamics, often people don't think about it, but in algebraic dynamics, it's I guess obvious to almost everyone here, but it's important to be able to describe good moduli spaces. So for instance, this morning we were talking about the space of rational maps and the moduli space of rational maps. And in fact, these are important spaces. Okay, I won't discuss that, but I think it's part of the problem. Second thing is, it's a regularity of conjugacy. Okay. When you say that a system is rigid, it's up to what? Okay. Here in the Cauchy problem, it's up to isometries. It's very good. Okay. In the Anosov setting, it's up to homeomorphism. It's very weak. Okay. And then if you want a smooth conjugacy, you have to impose that the conjugacy classes of the differential at the periodic points are conjugate. Okay. Then the third type of questions you may look at is extremality of dynamical fixtures. Okay. And this I won't discuss also, because I discussed that 20 years ago. Okay. Okay, so for instance, you know that if you have an endomorphism of PM, the projective space, of degree at least 2, then there is a unique invariant probability measure of maximal entropy. And this measure describes the equidistribution of periodic points. When is this measure smooth? So that's some kind of extremality, okay? Something which is not usual at all. Okay, this is the same as asking when are the Lyapunov exponents as small as possible. Okay. And of course, in fact, the most important question, which somehow takes care of all the previous one, is what is the minimal amount of data you need to recover the dynamics. So the pair, let's say the dynamical system. Okay, so you have let's say you have a map. Your dynamical system is just generated by one map from a space X to a space X. Okay, so that's the physical space. F is the law of evolution of your system. And you observe the dynamics of your transformation over time. Okay. And so you want to make a certain list of observations, and you want to say, okay, if I know that, for instance, if I know this orbit, or if I know the entropy plus this orbit, then I know the system. I know the phase space, okay, physical or phase space, and I know the evolution of it. So I know the map. Okay, and this is something in usual dynamics, you don't dream of such a statement. But what I want to say is that in algebraic dynamics, you have such statements, which were not yet proven 20 years ago, but which appeared since then. Okay, so I want to first, so I will split the rest of the talk in 3 little parts. And I want to, in the first 2 parts, I want to look at this last problem for algebraic transformations. And in the last part, I want to describe a recent result that we proved with Romain Dujardin, which is more related to the conjugacy problem, okay, to the first one. So I will focus on these 2 things. Okay. Okay, so here is problem 1. Okay. So here is an open problem. Let X be a complex projective variety. Let F from X to X be an automorphism. So it's an algebraic transformation of X. It's regular, it's invertible, the inverse is regular. Okay? So it's a holomorphic diffeomorphism of your complex projective variety. And assume that every orbit of F is dense in X. And the question is X an abelian variety? Okay. So here, just by some dynamical property, so here I'm assuming something on the dynamical property of F. It's some kind of extremal feature, but you observe the dynamics and you see that all orbits are dense. Can you recover the phase space? Okay. I'm not saying, I mean, an example is you start with an abelian variety and you take a generic translation on it. Okay, so you take a translation which is, which is generic with respect to the lattice such that the abelian variety is a quotient of a vector space by a lattice. Then all orbits are dense. Okay. So that's an example. I'm not saying that such an F has to be a translation. For instance, if you take x, y goes to x plus alpha, x plus y, on, let's say, C2, and you divide by the product of lambda by itself, where lambda is a lattice in C, such a transformation, all its orbits are dense as soon as alpha is generic with respect to lambda. Okay. So this is an observation by Furstenberg. But this is on a torus, okay, on an abelian variety. And this is true for surfaces, but this is otherwise I think it's wide open. And it's related to nice conjecture in algebraic geometry, related to abundance conjecture. Okay. So this is the type of problem, type of question you don't have in smooth dynamics. I mean, the analogous statement will be something like, you take a diffeomorphism of a surface, and you assume that all orbits are dense. Okay, then there are no periodic orbits. And then by the Lefschetz fixed point formula, the surface has to be a torus. I'm assuming the surface is closed, no boundary. Okay. Then the surface has to be a torus. So that's an analogous statement to this one. But this one is in any dimension, and I think it's much more difficult and interesting. I mean, it's not necessary to assume that the variety is smooth, because the singular locus is invariant. So if there were some singularities, then you take a point in the singular locus, and its orbit is not dense. So you know from the beginning that the variety has to be smooth. But I'm surprised that nobody asked what I mean by dense. Okay, here dense you can put what you want. What I mean is that some people ask this question for the Zariski topology, but even if you ask it for the usual Euclidean topology, then the problem is open. Okay, so the problem 2 is, let me start with a theorem. So it's okay, you take f, g, which are polynomial functions in one variable. Let's say degree of f is as, I think it's not necessary. No, it's not necessary. Okay, and you start with a point x in C. And so you look at the dynamics of f and g on the complex line, and you assume that the orbit of x under the action of f and the orbit of x under the action of g, their intersection is infinite. Then there are positive integrals a and b such that f to the a is g to the b. Okay, and the problem is what is the degree of generality for such a statement. Okay. For instance, can you prove something like that for endomorphisms of the projective space, where you replace the intersection is infinite by the intersection is Zariski dense in the projective space. Okay. And I want to demystify a little bit this theorem by proving a much simpler statement. And I'm realizing that here I should write it work with Romain. I write it before I realize that I won't have time to speak about what we did together. But this is part of something that we remarked when working on this type of problems. So let F and G be endomorphisms of the projective space Pm, let's say over Q bar, but it works over C of Pm, such that a degree of F is at least 2. Okay. And now suppose that there is a point X in Pm such that the orbit of F, the orbit of X under the dynamics of F is not far from being invariant by G. In the sense that this set is Zariski dense. Okay. Then there exists an integer R such that G is F to the R. What, Gabriel? When R is 0, G is the identity. Okay. And the proof? It's, so I will use what Antoine said this morning. So we have this notion of height for F. This is why I'm assuming that everything is defined over Q bar. Otherwise, I will use Moriwaki heights. But so there is a notion of canonical height for F, which I denote by H hat indexed. Well, I index by the map, not by the line bundle. Okay. And the distance between this height function and the usual veil height is uniformly bounded by some constant b on Pm of Q bar. Okay, as functions on Pm of Q bar. What is the next thing I need is when I compose, I just multiply by the degree of F, which I assume is at least 2. And then what next? X, you see, this orbit must be infinite because otherwise it cannot be Zariski dense. So the canonical height of X is positive because otherwise it will be preperiodic. And then the next thing I need is when I compose the usual height by G, roughly it's multiplied by the degree of G. So I can put the same constant B. Okay. Okay, and what is the meaning of this? So there are points xn in Pm. So xn is fn of x. So I parameterize points along the orbit just by the time corresponding to the dynamics under f. And so there are some integers n, not all of them, but some of them, such that, which are here, such that g of xn is also in the orbit. So it's f sigma of n of x. Okay. And now you compute the heights using these formulas. And you see that degree of g, degree of f to the n, and then there is a height of f minus degree of f to the sigma n. No. This is bounded by something that depends only on this error. So let's say 10 times b divided by the canonical height. Okay, you just compute the height of this point in two ways. You write that it is g of xn, and xn is fn of x. So this gives you this quantity. And you write that it is f sigma n of x. And this is. And now you see you just have integers here. Okay. And the fact that these are integers, it's easy to show from that sigma of n is n plus r for some fixed r and every xn in your set except maybe finitely many. Okay. But if sigma of n is n plus r, this means that g of fn of x is n plus r for some r. Okay, so this means that for this point, this is just fr of xn. And these points are Zariski dense. So g is equal to f to the r. Okay. Okay, so what I wanted to explain is that there are easy rigidity results which come from this dynamical heights. Which one is it? 3? No. 1? Yeah. Okay, so for instance, as an exercise, you can copy this proof, which I wrote on, for this easy proposition, and now you can look at another statement, which is the following one. Assume that there is T in N of positive lower density such that the fn of x for n in T is contained in the orbit of G under the action of x, the orbit of x under the action of G. Okay, and this set is Zariski dense in PM. Okay. So you make the same type of assumption, okay? But instead of saying that just the intersection is infinite, you say that the times at which this intersection is non-trivial occur along a set of integers which have positive lower density. then you get the same conclusion. Okay, and it's exactly the same proof. You just compute heights. So there are very easy statements that you can get from this height computation. But the type of statement that Gyoka, Tucker, and Ziv obtain it's much harder because because it is so. Okay, and so for instance, I think we don't know yet how to extend this to endomorphisms of P1 instead of polynomial map in one variable. So rational fraction, I think it's not done yet. Yeah. Oh, now it's true? Okay. Oh, sorry. Sorry, I changed my talk roughly during lunchtime to fit it better with Antoine. Okay, thank you very much. Very nice. Because I wanted to talk about automorphisms, but Antoine did not introduce a canonical height for automorphisms. So. Okay, so the problem is it true? Such a statement true for automorphisms of K3 surfaces. Okay, this type of statement. Okay, and the best I know in this direction is it's a theorem that Mark obtained is for automorphisms of affine surfaces, let's say, normally reducible affine surfaces, with which have a dynamical degree which is larger than 1. If you prefer, if you work over the complex numbers with positive entropy. Okay, and the statement is initial one. So if you take two automorphisms and an orbit, a point and the two orbits, they intersect infinitely many times, then automatically it's, the intersections are Zariski dense, and the automorphisms, they have common powers. Okay. And it's completely uniform. It works for all affine surfaces. Okay. Now I move to what I did with Romain. And it concerns regularity of conjugacy. Okay. So let me start with the easiest theorem we proved. It's as follows. Let F be an automorphism of the affine plane, let's say C2, with positive entropy, or if you prefer a dynamical degree larger than 1, or if you prefer, it means that F is conjugate to a composition of Henon mappings. Assume F is conjugate, so it's conjugated to an automorphism G of the plane by a holomorphic diffeomorphism phi. Okay, so the conclusion is that yes, it's an algebraic automorphism. Everything is algebraic, but the conjugacy is only a B holomorphism. Okay, so the assumption of F and G, both of them are algebraic transformations, but the conjugacy is only assumed to be holomorphic. Then, in fact, phi is an automorphism. Okay. Okay, so it's this type of result that if you start with some conjugacy, then you can automatically improve the conjugacy. Okay, so you start with something which is just holomorphic, so maybe you use an exponential function. In fact, no, you couldn't. Okay. So this is the first strengthening of regularity that we obtained. It's the easiest statement. And then, in fact, you can choose phi to be, I mean, then maybe you have to change phi by composition with F, but you can choose phi to be of degree bounded by some explicit formula in the degree of F and G. Okay. And so this opened our study of this type of rigidity. So you start with some kind of conjugacy, and you want to say that in fact the transformations were conjugate inside the group of polynomial transformations. And so on. So same assumption for F. Okay. And you take another polynomial automorphism of the plane. And what we obtain, so at the moment the best we can do is if F is conjugate to G by real analytic diffeomorphism from C2 to C2, so viewed as a real analytic space. And then we need a little extra assumption, and F has a saddle periodic point P. So F to the n maps P onto itself for some n. And you assume that the two eigenvalues such that, I mean, the eigenvalues of the differential of F at P are complex but not real. Okay, so each of them is a purely complex, I mean, not real as number. Then F is conjugate to G, or maybe to the complex conjugate of G inside the group of automorphisms of C2. Your conjugate, I mean, phi of, or the complex conjugate of phi has to be a polynomial transformation. And this result, in fact, is part of a series of rigidity statements. So as the theorem I mentioned in the introduction, in fact, it's not just one statement about improving regularity of conjugacy. It's a bunch of statements about rigidifying objects which are invariant. Okay, so for instance, which one do I want to state? Yeah. So F is Henon map as here, F does not preserve any real analytic foliation of C2 by complex leaves. So this type of statement enters into the proof of the theorem. Another one is if you look at J plus, so the Julia set in positive time, so the boundary of the set of points with a bounded forward orbit, and you intersect with a transversal disk. So this set has a structure of a laminated space. So you slice it non-trivially and transversally. This is never a curve. Okay, let's say a smooth curve to make it clear, but even a rectifiable curve. Rectifiable curve. Okay, which means, so this is a good analogy for the Julia set for transformation in dimension 1. In dimension 1, you have the examples of, let's say, monomial transformations and Chebyshev maps, or Blaschke products have this type of properties. There is no example like that in the setting of automorphisms of C2. Okay. So here it's a non-existence result. So the extremality I was talking about at the beginning of the talk, you know, that the Julia set, I mean, this version of the Julia set is a smooth curve, never happened. Okay. Okay. I think I have to stop, so I stop.
We have time for a quick question.
So in the theorem, I would have expected dynamical degree greater than 1, but you said greater than.
Oh yeah, yes. It's because for polynomial automorphism of C2 with dynamical degree greater than 1, the map is conjugate to a composition of Henon maps, and the dynamical degree is in fact the product of the degrees of these Henon maps. So being strictly larger than 1 is the same as at least 2. Okay. Okay. And of course, also I stated like a problem. It looks like it's not a problem anymore because I stated theorems. In fact, of course, you want to improve somehow this type of results. Okay. Real analytic is quite strong. Can you improve it by looking at smooth conjugacies? Or can you prove it in the context of automorphisms of K3 surfaces or things like that? Which should be easier, I think. But
one quick question.
Yeah. So why did we introduce the notion of positive density instead of?
Oh yeah, I wanted to say that there is a statement that you can get for free, which goes in the direction of. So I should. Sorry for that. I'm very confused. Okay. There is a version of that you can get for free using, when I say for free, it's using this type of argument. It's the following. You just assume that this infinite number of points that you get correspond to a subset of times in the parametrization by f to the n, which has positive lower density. If you assume that, then the statement is somehow obvious with this thing. That's what I wanted to say. Okay. Sorry again.
Let's thank Serge again, and then we resume in 10 minutes.